So I was looking at the wood again, and there's so many different wood. However, we see some similar patterns, and this is another really common one that I see quite often. Where you have these vertical or horizontal lines, and they're a bit different from our Gaussian. If we remember, we were talking about the Gaussian, and the Gaussian gave us these drips. They almost look like these drips, and I think I have one of the previous ones open. Yeah, let's see. That's not it. Might have erased it. Oh, that's cool. Oh, maybe I wasn't working with this one. Oh, I was working with this earlier. This is our e to the y cosine of x. I might just leave that on there for a second. That's really nice. This is one of my most favorite shapes. They're mathematical expressions based on Euler. I have a function I can show you later on. And when we start building our functions, it's really imperative that we write out the mathematics correctly. And we got to start with the basic principles, and one of those include our Euler. We have to build our own Euler. So that's pretty much what that is our Euler, and it's really quite beautiful as a mathematical expression in nature. And to get it to look like this, what I did was this is the shape as it is. This is exactly where the mathematics would be found, and it's really quite beautiful. This is something that you would find in DNA, for example, or in the nuclear aspect of, or I should say not nuclear, but in the aspect of how a helix might move. E to the x, or in this case e to the y, is a phenomenal function because it's going to increase by a step of 1, and for each index, and as the index increases in its position, it's going to also increase the denominator and the numerator. Well, it's going to increase the numerator by 1, but it's going to increase the same denominator by 1 factorial, by the factorial, um, which, pretty much compounds by quite a bit. Anyway, yeah, really quite beautiful. Oh, I just applied lines here, the line and then the color, and I think I changed the opacity as well, but I didn't do anything else. It's pretty quick. Um, Trying to remember, it might not have been this one then. Maybe I closed it. Pretty sure it's where it was. It was probably this one, and I just ended up changing it. 10 to ex squared. Oh, that's what I did. It's our perspective. Sorry, it took so long. Basically, this is what I was talking about there um, for the other expression that we were talking about in a tree, something like that. So, based on Gaussian, this is on a three-dimensional axis, three-dimensional plane here, and versus this one, which is our two-dimensional graph. But this is the exact same graph as this other one. And if you take a look, I changed this a little bit, I think. Maybe not. Maybe I didn't change it. I guess I didn't change it. Maybe I thought I did. Maybe I changed this one. Oh, did I change this one? Well, I didn't change this one either. Well, anyway, what I was doing is I was working a little bit on changing some of these units here, and they're not units, but basically substituting it for what it really is or where it really comes from. So, for example, some of these, this is a good one to look at. This is what I created just with this expression here. So our x to the pi, and this is our source light. This is basically what's going to give us our real, this is the real what it is. And I didn't define the equal, I just gave it this so that it would calculate it for me. And this is the outcome the output that it gave me. But basically, this is quite interesting, and I'm going to create a whole nother worksheet on this and show you the proof and show you the mathematics, and then maybe create a video. But basically, I have a negative here, but really it's I. It's going to be I squared. But if you know I is the square root of -1. So if you square the square root of -1, then you take care of the square root, and you're left with just -1. So that's where I got that. And I didn't just get this anywhere either. I was working on my cosine function so that when we use cosine, everything's correct. Basically, that's where this comes from here. Look, just usually we have to sit with this for a little bit to really understand it. But this is squared and that's squared, so because this is going to be the trigonometric identity that we're going to work with quite a bit. And I think I might even have one somewhere. Might have been talking about it earlier. See if I have well, it doesn't really matter right now. Point is, that's where I kind of got that expression from. And I figured out here we have the angle that we're going to substitute, we're going to define in the beginning. So if we type in cosine of 45 degrees, then it's going to give us our output. And here first it has to convert our angle to radians, so that's where I get that from. And I have a string that I keep. It's 1,000,000 digits of pi, and then that's going to be divided by 180, divided by basically divided by the value, the real value of pi. So I mean, this is what is equal. 180 is equal to pi. So, but this gives us the actual ratio of what we're working with. So that's why we get 180 degrees to pi. Pi is going to be that 180 degrees. 2 pi is going to be 360 degrees. So that's where we get that from. But this is where we get our I from. So at the very beginning, we're defining t, and in this case, t is equal to 1. And I suppose that you could change the value for t, and I think that's what I might have even done at some point, but probably not, because generally you're going to want to work with the standard unit circle. But anyway, this is, t is really talking about I, it's really referring to I. So this, before it was expanded, you can't really include I in here. Now here it says for I and 1 to n, but that's a different I. That's going to be, well, that's another I. I mean, it's all the same I. You know, when we looked earlier, that's our unit for time, 1 to n, and n is defined as 4, just as we did here. He did the same thing. I got this from somewhere and then kind of changed it around to suit my needs. But basically, that's where you get that from. But this is really t. This is really I expanded, or unboxed, I should say. This is I unboxed, and then our n equals 4 is going to be our I, or this whole thing is our I. It's our I in the box, but the bigger box, the real box of time. But this is our imaginary I, and that's why we can't really write that in there, because there is no. So you type in the square root of -1, it's not really gonna give you I. So that's why we square that, and we square the whole thing. But that's why there's another angle here. This was squared. It doesn't show you what it was before, because then you would have to include I, and then you can't really define that. So basically that's why it's squared. And the bottom is squared also. This used to be the square root there, and that's why we have the square root there. We try to preserve it, try to bring it to the beginning, and then kind of work our way to show you where we get the numbers from. But anyway, square root of 2, and I gotta look up what this is. In this case, we called it, well, let me think. T, I think. No, I. It's called I. Oh, okay, okay. Yeah. 2 times I minus 1. Okay, so that's I. We could call that I as well, but I don't want to really call that I because then, well, I guess I should call it I actually, and in truth, I should probably call that I, so maybe I might do that a bit later. So let's just call it I for now. So I equals 1 to 4, so the range of 4, increasing by a step of 0.2, and you can see, we have these nice points here. If it fills it in, and that's something that we're going to want to write also. We're going to want to create a for loop just like this for I and 1 to 4 just like this, but we're going to want it to create our point set also, which we can write to a nice table or write to a nice text, and I'll show you what that text looks like real quick. Generally, one of the first texts we're going to want is I think it's in here. I forget what I called it. Oh, I called it by where I got it from. Pretty sure. Oh yeah. Okay. So basically, something simple where you have each data point separated by a space, and the reason why I do that is because if you take a look at when we write out more what it's going to do when it reads the line, it's going to read the line, but then it's going to write a prefix and a suffix as well. So when we do our arrays, when we build our arrays, we're not going to want to have any errors. So the first thing we want to do is, we're going to write, let's say list 1 equals 0, 0, 1, and list 2 equals 1, 1, 2. But remember, you can't put a list in a list. It just doesn't work with the system. So essentially, what we're going to want to do is we're going to want to say, okay, well, give me the first position of the first list. And it says, well, that's 0. And I say, okay, well, give me the third position. And it gives me that quite nicely. So what we're going to end up doing after we store these is we're going to want to store these individually and then build our arrays after that. So basically, we're going to say list 1, 1, let's say something like that. And we can't put a space there for working with our bash. We'll make sure we understand, go over the syntax of where you can put a space and where you can't. And in this case, we just want one space. You don't want to put a comma. You don't want to put a comma. You don't want to put anything else. Just one space to separate out the items in our list. And basically, this is going to be list 1, 1, 1 is going to be list, or make sure we do our reference symbol, list 1, 1. So that's basically all that is. And then we can kind of do the same thing for the next one. And what this does is it stores it individually. And we do that also when we're working with our cosine, is we're going to store each one individually. As you can see here, I have a cosine 1 equals the sum, and then that way when we work with the sum later on, we stored it as cosine 1, and then we can kind of look at the running sum instead of having to worry and store each one as as that version for that to that variable. So but here anyway we have, let's say, list 1 combine, or let's say list 1 or A maybe for array, and then we're gonna do list 1, or sorry, this, maybe we'll do it like this, yeah. Maybe we'll put it in a string also, I don't know, I want to think about it. First, just do list 1, oh, we gotta do a reference, list 1, 1, and then we do space, and yeah, okay, list 1, 2, I probably should have checked to make sure this works, but it should work. Yeah. So anyway, then when we echo, or when we call our new array, it'll give us the combination quite nicely. Now, if we try to put the list in the list, it wouldn't really work. But when we rebuild our arrays, we always want our arrays. We don't want to. We want our lists to be stored like this as our columns and our rows. But when we go over here and we're storing it, first we're gonna set it up so we can actually work with it. You know, because if I have this line there, first I have to store the whole line. That's the best way to store the whole line. And then we're going to want to isolate each item within the column. And remember, for each row, I should say, we're going to want to isolate the item for each column and store it as an individual variable, and then build all of our arrays as upon that, so that whenever we're working with our numbers or our data frames, we're not working with our lists anymore. We're working with the arrays that we build as you know, for every upon command, I should say, basically. So the arrays aren't built until you build them, and then it'll store each version of that array. So if you change an array, you can always go back to a previous version if you want. And it just makes it a whole lot easier. Anyway, right. So anyway, going back to the main point here. We said we're going to change this to I. Let's go ahead and do that. Change that to I. Change that to I. And it should give us the same. Yeah, okay. But then I don't know where my other stuff is, you know, so I don't know what happened there. Maybe we don't want to use I. But that's pretty cool. You know, there's a difference, it says, between using I and using, as you can see, you know, one is going to be in front of the other. So I don't know. I might have to look and see why that might be. But for now, let's just use this. And we can always substitute for I later on. And that's just something really nice. Anyway, main point here, we're talking about the lines. And I was trying to figure out where it got those from. Oh, I guess it doesn't make a difference. Alright, so in that case, we'll just use I. Sorry. Let's see. And it's really important what variables you choose, because, you know, it's going to be what it's going to, like, you don't want to confuse a variable. You don't want to accidentally. So, always take your time with these. Anyway, point is, we're working with this graph right now. So anyway, let me take off the Gaussian. So this is pretty cool, because what I did was I basically translated, I basically translated each of these, and some of these have T that's supposed to be an X though. Put T there, but or not. It's not. It's supposed to be I, so it should be I minus pi, and that should be I since we just established it to be I. So I will change that later. That should be I, and then that should be I, and then but this should be X. So that's a huge difference. Is we're looking at this, and it gives us our horizontal, and we were saying that that's I. I mean, it could be T, but T, it should be continuous. So, I mean, in this case, it is continuous, but it's not, because it's from point 1, point 2, point 3. That's not really continuous. But this is continuous. So instead of using a variable that isn't known in the system, in the coordinate plane, In the coordinate plane, we're just working, in this case, we're working with x and y. We have our vertical y, our horizontal x. So that's why we say 2x minus pi to the 4. And pi to the 4 is, we can change that if we wanted to. We could say, well, I don't want to use pi over 4. Pi over 4 is 45 degrees. Maybe I don't want to use 45 degrees. Maybe I want to use 90 degrees. So it should look a little bit different. Let me see if I can isolate it. Okay, so that's that one. Let's see, maybe just use pi. Let's see what that does. I'm hoping for an expansion, but as you can see there, that's quite interesting. So pretty much the rules don't change too much. You can use pi over 4. You can use, in this case, let's say we use 2 pi and see what that looks like. Still just shifts it over. Pretty sure that's what happened. Let's see. Oh, doesn't really shift. Maybe 0.5. Yeah, okay. So basically, we want to figure out, well, what is our horizontal, what is our vertical shift? Right now we don't have any vertical shifts. On this one I have a vertical shift, -1. I also have it shifted from the get-go using -y. But you could also do +1, +2 to give you that vertical shift, or you could mess around with that. So this kind of gives you an idea of how to set up where the reference points are. So if you wanted to do like, you know, instead of doing -1, maybe you wanted to do reference vertical shift or something like that. Maybe I should do shift vertical. So, you know, something like that. So we have an idea of how we want it to move up or how we want it to move down. And then for the horizontal, we just saw that we were using the pi. We said x minus pi over 4, and x references our horizontal axis. So it makes sense if we're going to say x minus something, then it should go in that direction, or, you know, it should go in that direction, depending on what it is. So pi over 4 is basically the degrees. We can't just type in x minus 45. It's not really going to tell us anything. So our pi over 4 is going to tell us what the actual unit should be. So anyway, the reason why this is really important is because, as you can see here, I could isolate just one portion, so you have an idea of what I'm talking about. Let's see. I want to use one that is already preset. Okay, that's a good one. So basically, as you can see here, in the tree we observe this, but what is actually, but as you can see, if we compare, this is x, whereas this was, you know, this was I. In this case, we used a different one, but this would be I, and that's what's super cool is, or I mean, you can use whatever you want, I guess. So, but you know, as you can see here, the maximum and the minimum are the same. Each one of these lines is iterated or is created by this portion, this range. But instead of creating a wave, it just does the straight line, and that's because it's not continuous. So it's just gonna be, you know, since it's defined as that fixed point on here, so it's defined as 0.1 or 0.2, 0.3. And as you can see, then we get to 2, 2 goes there, 2 goes there, and it increases there. But it was interesting as you go 1 starts there, and then you go 1.1 goes down. If you go 2, goes 2, and then it goes up. And so as you can see there, the up and the down is going to be our direction here. So as you can see, the sine, I mean, that's what it is. The sine wave, the sinusoidal function is creating these horizontal planks, I should say, these sort of uh, um, light, what do you call them? I don't know, whatever you want to call those. But basically, that's really was quite beautiful, and you see that in the wood. Because for it to then have, because we were looking earlier, we defined the Gaussian as this, so we did set this up already. This is already, you know, established. But in conjunction with this, or maybe in some wood instead of that, it uses this one. So, or it uses, you know, this one. But you don't see this part. You don't see that. You see it as this. But then in the actual overall, you see it as this. So, or it converts this and creates this. So, this is super nice. I mean, we're looking at how do we kind of continue drawing our mathematics and our functions, and being able to draw our waves is really important. And one thing is we're going to want to figure out how to expand this portion, and most likely it's just a matter of zoom. I think if I zoom in, it should, maybe not, but that should be the factor, is if you just scale it. But I think that the nature of the cosine and the sine doesn't really change shape, but what's interesting is the way that it looks like this, and but it's based off of a circle. However, when you're looking at the graph, like this, you can only look at it like you have it's cut in the middle there, but then you have this sort of stretch there, and you have this sort of stretch there, but it is essentially a circle. But the reason why it looks like that is that perspective lens. You know, we got to remember, you look at the z-axis says 1.054, this is the axis is 1.75, this is the axis is 0.1. So it does change the z, just as you would expect, you know, over here when we're looking at this portion. So, but that's what's really quite interesting, is we can never forget the, because this is all circles also, but you can never forget that if we tilt this on the two-dimensional graph, that we'll see the circle, but in true reality, if we were to draw it on a two-dimensional, this is what it would look like, something more like this, because that's what the perspective tilt would look like with this particular range set up. At least that's what I think. I don't know. I have to explore more and see. You know? But basically, what we really want to do is be able to reference these and make sure that these outputs are always built with those tiny little functions. And I'll show you later how we're going to lay that out to make that simple. All right.